Look up at the night sky on a clear, dark evening. You see a tapestry of brilliant stars, distant suns that have guided explorers and dreamers for millennia. It feels complete, like a map of our cosmic neighborhood. But what if I told you that map is missing entire chapters? What if, hidden in the vast, silent blackness between those twinkling lights, there are entire worlds right in our cosmic backyard, so dark and profoundly alien that our most powerful telescopes can barely even sense they are there? We are not talking about distant galaxies or theoretical oddities. We are talking about planets, but not as we know them. These are the Y-class planets, mysterious bodies that defy our simplest definitions and lurk in the perpetual shadows of space, forming a hidden population of cosmic ghosts. Imagine a world where the sun never rises, where the very concept of daytime is a fantasy. A place where the temperature is so bitterly cold that it makes the frozen plains of Pluto feel almost tropical. These are not the rocky, Earth-like worlds we hunt for in the habitable zone, nor are they the blazing gas giants like Jupiter. They are something else entirely, a class of objects so strange they blur the line between a failed star and a rogue planet, wandering the void alone and unbound. Their existence challenges everything we thought we knew about planetary formation and what it means to be a world at all. In this video, we are embarking on a journey into the darkest, most elusive corners of our galaxy to hunt for these shadow worlds. We will explore how scientists even begin to find objects that emit almost no light or heat, unpack the bizarre physics of their ultra-cool atmospheres, and confront the mind-bending question of what kind of life, if any, could possibly survive in such profound isolation and darkness. This is a story of cosmic secrets hiding in plain sight, a testament to just how much we still have left to discover. So get ready to peer into the shadows, because we are about to explore the strange and chilling reality of Y-class planets. So to understand these shadow worlds, we first need to answer a fundamental question. What exactly is a Y-class planet? The term itself comes from the complex language astronomers use to classify stars and star-like objects based on their spectra, which is essentially the unique fingerprint of light they emit. You have familiar classes like G-type for stars like our Sun, or M-type for smaller, cooler red dwarfs. But at the very coldest, darkest end of this cosmic temperature scale, beyond even the L and T classes of warmer brown dwarfs, we find the Y dwarfs. This is the official classification for the coldest known substellar objects in the universe. Calling them planets is actually a bit of a simplification that hints at their mysterious nature. In reality, a Y-class object is a type of brown dwarf. Think of a brown dwarf as a cosmic in-between. It's an object that gathered too much mass to be considered a planet like Jupiter, but not nearly enough mass to ignite the sustained fusion of hydrogen in its core that defines a true star. It's a failed star, a cosmic ember that glows faintly with the residual heat from its violent birth, slowly cooling over billions of years. The Y-class represents the final, coldest stage of this cooling process. Their temperatures are almost incomprehensibly low. While a star like our Sun has a surface temperature of thousands of degrees, the surfaces of Y dwarfs are so cold that their temperatures can be comparable to a warm summer day on Earth, and in some extreme cases even colder than the human body. We are talking about objects in the void of space with temperatures you could theoretically touch without being burned. This profound cold is the primary reason they are so dark and difficult to detect. They emit almost no visible light and only a faint whisper of infrared radiation. This leads us to the great blurring of definitions. If a Y dwarf is floating freely in the darkness of interstellar space, untethered to any star, is it a brown dwarf or is it a rogue planet? The distinction becomes incredibly hazy. Traditionally, we think of planets as objects that form in a disk of dust and gas around a young star and then orbit that star for the rest of their lives. But many white dwarfs are solitary nomads. They may have formed on their own like a star from a collapsing cloud of gas, or they could be planets that were violently ejected from their home solar systems in the gravitational chaos of their youth. When you find a lone, planet-sized object with the temperature of a cloudy day, the line between a failed star and an exiled world becomes almost meaningless. They are, in essence, the ultimate celestial ghosts, massive enough to be born from star-like processes, yet cold and dark enough to haunt the cosmos like the most lonely of worlds. Given how incredibly cold and dark these objects are, you can probably guess that finding one is like trying to spot a single, unlit charcoal briquette floating in the vast emptiness of space from thousands of miles away. The primary reason for this immense difficulty comes down to one simple, brutal fact of physics. They emit almost no light of their own. Unlike stars, which blaze across multiple wavelengths, white dwarfs are cosmic dead embers. In the visible light spectrum that our eyes use, they are utterly and completely black. If you were to fly right past one in a spaceship, you wouldn't see it with your naked eyes until you were practically on top of it. All of our traditional methods for finding planets, like watching for the telltale dip in a star's brightness as a planet transits in front of it, are useless here because these objects aren't orbiting a bright star we can monitor. They are solitary, adrift in the dark, so if they're invisible in optical light, where do we even begin to look? The answer lies in the faint, residual heat they still possess. All objects with a temperature above absolute zero emit some form of electromagnetic radiation, and for something as cold as a white dwarf, that radiation is almost exclusively in the form of long-wavelength infrared light. Think of it as the heat signature you feel radiating from a warm road long after the sun has set. This is their only discernible fingerprint on the cosmos, an incredibly faint whisper of warmth against the cold backdrop of the universe. But even in this part of the spectrum, they are excruciatingly dim. The hottest white dwarfs might glow with the intensity of a candle seen from the distance of the moon, while the coldest are more like a match flame viewed from thousands of miles away. Our own atmosphere is a major obstacle, as water vapor and other gases absorb much of this specific infrared light before it can ever reach telescopes on the ground. This is why the hunt for these objects has required a new generation of space-based observatories, designed specifically to see the universe in this elusive thermal glow. For years, missions like NASA's Wide Field Infrared Survey Explorer, or WISE, provided our first tantalizing hints of this hidden population. By scanning the entire sky in infrared, WISE was able to identify a handful of the very coldest brown dwarfs, some with temperatures shockingly close to that of our own planet. But even for a powerful instrument like WISE, detecting these objects was like trying to hear a pin drop in a hurricane. The signals were so incredibly weak that they pushed the technology of the time to its absolute limits, and many likely remained hidden in the noise. The data suggested these dark worlds might be far more common than anyone had predicted, but actually confirming their existence and studying their properties required a telescope with unparalleled sensitivity, one that could dwell on a tiny patch of sky and gather every single precious photon of infrared light. This is precisely where the James Webb Space Telescope enters the story, acting as the ultimate instrument for this cosmic ghost hunt. Orbiting far from Earth's interfering heat, and equipped with a massive gold-coated mirror and exquisitely sensitive infrared detectors chilled to within a few degrees of absolute zero, JWST is the first observatory truly capable of not just finding these shadows but studying them in detail. Its vision is so sharp and its instruments so sensitive that it can finally pick out the faint thermal glow of even the most frigid white dwarfs. It can dissect their faint light to analyze their chemical composition, searching for the signatures of molecules like methane, water, and ammonia that dominate their ultra-cool atmospheres. With JWST, these objects are transforming from theoretical phantoms into real worlds we can begin to understand. Every new white dwarf it discovers is a testament to human ingenuity, a reminder that to uncover the universe's deepest secrets, we sometimes have to learn to see in the dark. To truly appreciate just how extreme these white dwarfs are, it helps to see them not as isolated oddities, but as the final, coldest members of a very specific cosmic family, the brown dwarfs. Think of this family as having its own temperature chart, a spectral sequence that classifies these failed stars based on how much heat they still radiate. At the warmer end of this scale, we have the L dwarfs. These are like celestial embers fresh from the fire. They're still hot enough to glow a faint, dull red, and can even have molten iron and silicate clouds raining in their atmospheres. They are the fading twilight of a star's potential. As we move down the temperature scale, we enter the domain of the T dwarfs. Here, the heat has faded significantly. The atmospheres become cold enough for methane gas to form, which gives them a distinct chemical signature. If you could see one, it might appear with a faint magenta or deep purple hue. They are the smoldering coals of the cosmic fireplace, still holding onto a noticeable warmth but no longer with any visible glow. And then, at the absolute coldest, darkest end of this spectrum, we find the Y class. If a T dwarf is a smoldering coal, then a Y dwarf is that very same coal hours later, when it has cooled to nearly room temperature. All the vibrant heat and faint light have vanished, leaving behind an object that radiates only a whisper of residual warmth. This is why the jump from T class to Y class is so profound. While a T dwarf might still have a temperature of a few hundred degrees, the surface of a Y dwarf can be colder than a winter day on Earth, with the most frigid examples measured at around -80 degrees Fahrenheit or even lower. At these temperatures, their atmospheres become dominated by more exotic chemistry, with ammonia clouds likely forming and even water vapor condensing out to create water ice clouds in the skies of a sunless world. This incredible cold is what makes them the ultimate ghosts of the brown dwarf family. They possess so little energy that they represent the final stage of a brown dwarf's long cooling process, a quiet, dark retirement that lasts for trillions of years. So when we talk about discovering a white dwarf, we are essentially finding the oldest, most retired, and most elusive members of this celestial clan. Objects that have shed almost all their birthright heat and now drift in a state of near-perfect cosmic chill. The discovery of these shadow worlds wasn't a sudden event, but a slow, painstaking process of elimination, sifting through mountains of data to find the faintest of cosmic whispers. And it was NASA, a wise telescope, that first gave us the tools to begin this search. While earlier surveys had identified the warmer L and T-class brown dwarfs, the coldest ones, the Y dwarfs, remained purely theoretical, that is, until the data started revealing anomalies. Among the first and most startling of these detections was an object catalogued as Ys 1828 plus 2650. When astronomers analyzed its infrared signature, they were met with a reading that defied belief. Its estimated temperature was around 80 degrees Fahrenheit, a comfortable room temperature. The idea that an object floating freely in the dark of interstellar space could share a temperature with a summer afternoon on Earth was nothing short of revolutionary. It was a moment that instantly redefined the boundaries of what a planet-like body could be. Here was something with the mass of a giant planet, yet it was utterly alone and astonishingly temperate. The astronomical community was electrified by a mix of excitement and profound surprise. This wasn't just another data point, it was a glimpse into an entirely new class of celestial object that had been hiding in plain sight, forcing a complete re-evaluation of our cosmic senses. But if Ys 1828 was a surprise, its successor was an even bigger shock to the system. A few years later, another Ys discovery captured the spotlight, Ys 0855-0714. This object wasn't just cool, it was positively frigid. With an estimated temperature of about -10 degrees Fahrenheit, it became the coldest brown dwarf ever identified outside our solar system. At the time of its discovery, it held the record as the fourth closest known system to our Sun, a cosmic neighbor we had completely overlooked because of its profound darkness. What made WISE 0855 so particularly fascinating to scientists was the strong evidence for water ice and water vapor clouds in its atmosphere. Think about that for a moment. Here is a world with no sun, adrift in the void, yet it possesses the same basic ingredients for clouds that we have here on Earth. The profound implication was that the atmospheric processes on these solitary worlds could be far more complex and dynamic than anyone had dared to predict. They weren't just simple, frozen balls of gas, they had weather. The detection of these water clouds was a landmark achievement, suggesting that even in the absolute coldest and darkest of environments, the universal laws of physics and chemistry can conspire to create environments with startling parallels to our own home planet. Confirming the existence of these pioneers was a monumental challenge in itself. Their infrared signals were so incredibly weak that initial detections were right on the very edge of what the WISE telescope could reliably see. For WISE 0855, astronomers had to combine dozens of individual images, a process not unlike a long photographic exposure, just to gather enough of its faint light for a confident analysis. Even then, they could only observe it in a limited range of infrared colors. It was like identifying a person solely by their silhouette in a pitch-black room. You know someone is there, but you can't make out any of their features. This fundamental limitation is what made the subsequent role of the Spitzer Space Telescope so critical. Spitzer, with its more sensitive infrared camera, was able to perform follow-up observations that helped to pin down the temperature and distance of WISE 0855 with much greater precision. It was the combination of these two space observatories, WISE as the wide area scout and Spitzer as the focused investigator, that finally cemented the reality of the White Dwarf class. They proved that these dark worlds were not just statistical flukes, but real, physical bodies that we could begin to study, opening up a whole new frontier in the exploration of our galactic neighborhood. But let's take the next logical and perhaps most thrilling step in our exploration. We've found these shadow worlds, we've classified them, but what would it actually be like to be there, to stand on the surface of a white dwarf? The experience would be unlike anything depicted in most science fiction, a confrontation with an environment so profoundly alien it challenges our very understanding of what a world can be. First, forget the concept of a solid surface as we know it. A white dwarf, like the gas giants in our own solar system, doesn't have a distinct rocky ground you could land a spacecraft on. Instead, you would find yourself descending through an atmosphere that gradually thickens from a thin haze into a deep, soupy fog, eventually turning into a dense, fluid-like state of molecular hydrogen. There is no shore to this ocean of gas. You would simply sink deeper and deeper into the eternal darkness, and that darkness is absolute. Imagine a twilight so deep it is indistinguishable from midnight, a blackness so complete your eyes would never adjust because there is literally no light to see. High above, if this white dwarf orbits a distant star at all, that star would appear as nothing more than an exceptionally bright pinpoint, a brilliant but useless star in a sky otherwise devoid of any other celestial bodies. There is no sunrise, no sunset, no direction to the passage of time except for your own heartbeat. The only illumination would come from within the atmosphere itself, and even that is barely perceptible. On the very hottest white dwarfs, you might witness a faint, deep crimson glow caused by disturbances in the atmospheric layers, a haunting ember light that only makes the surrounding blackness feel more oppressive. On colder varieties, the only light might be the occasional silent flash of lightning within the exotic clouds, briefly revealing a landscape of swirling, impossible vapors. Speaking of clouds, the skies of a white dwarf are where the true alien chemistry unfolds. We're not talking about simple water vapor clouds like those on Earth. At these incredibly cold temperatures, the atmosphere is a chemical factory for bizarre meteorological phenomena. As we saw with WISE 0855, water vapor is present, but it condenses into clouds of water ice particles, creating a blizzard of snow that never reaches a ground. Deeper down, you might encounter vast decks of yellowish clouds made not of water, but of ammonia ice. And for the most exotic varieties, theoretical models suggest that in slightly warmer white dwarf atmospheres, you could find clouds made of salt, sodium chloride, and potassium chloride, or even compounds like zinc sulfide, raining a dusty, sand-like particulate through the atmospheric layers. It's a world where the very air you breathe, if you could breathe it, would periodically condense into a rain of salts or sands, falling endlessly into the abyss below. Then there is the force of gravity. While not all white dwarfs are the same size, many have masses several times that of Jupiter. Standing on the nebulous surface, where the atmospheric pressure equals that of Earth's at sea level, you would be crushed by a gravitational force many times stronger than what we experience. Every movement would be a Herculean effort, your body feeling impossibly heavy, your every breath a struggle against a weight that pushes down on you from all sides. This immense gravity is also what helps create such a stratified and layered atmosphere, trapping heat and chemicals in a deep, global blanket that contributes to the strange and complex weather patterns. Ultimately, the atmosphere of a white dwarf is a place of violent stillness. While the upper layers might be subjected to ferocious winds, driven by the immense temperature differences between the perpetual night and any faint internal heat, the experience at depth would be one of immense pressure, profound silence, and a cold that seeps into your very soul. It is a world defined not by the fiery processes of a star, nor by the geology of a planet, but by the slow, patient, and bizarre dance of chemistry and physics in the deepest cold of space. It is an environment that is simultaneously horrifying and magnificent, a testament to the sheer diversity of worlds that the universe has to offer, even in its darkest and most forgotten corners. This brings us to a fundamental and surprisingly heated debate in astronomy, one that strikes at the very heart of how we define our universe. What do we actually call these white dwarfs? Are they failed stars, or are they the most massive and mysterious rogue planets imaginable? The answer is not straightforward, and the disagreement forces us to confront the limitations of our own cosmic vocabulary. On one side of the debate, you have the traditionalists who argue for the classification of failed star. Their reasoning is rooted in the genesis of these objects. A brown dwarf, including the Y-class, forms in exactly the same way a star does. It begins as a collapsing cloud of gas and dust, gathering mass under its own gravity. The key difference is that it simply never accumulated enough material to reach the critical mass threshold, about 80 times the mass of Jupiter, to ignite sustained hydrogen fusion in its core. It is, by its very origin story, a stellar object that didn't quite make the cut. From this perspective, calling a white dwarf a planet is like calling a sapling that never grew into a tree a kind of rock. It misrepresents its fundamental formation process. The other side of the argument, however, points to the extraordinary physical characteristics of these bodies, which look and behave nothing like any star we know. When you examine a white dwarf, its temperature, its atmospheric chemistry, and even its potential for cloud formation are far more analogous to a gas giant planet like Jupiter than to any star. A star is defined by its internal fusion engine. It creates its own light and heat. A white dwarf, especially the coldest ones, has no such engine. It merely radiates away the leftover heat from its birth, slowly cooling into oblivion. Its energy budget is planetary in nature. Furthermore, we know that gas giants can form in two ways. They can coalesce from the disk of material around a young star, which is the standard model, or they can form directly from the gravitational collapse of a gas cloud, a process that blurs the line between planet and star. If a Jupiter-sized object forms alone from a collapsing cloud, is it a planet or a brown dwarf? The distinction becomes almost philosophical. Proponents of the rogue planet view argue that if it looks like a planet, has the temperature of a planet, and possesses an atmosphere with planetary weather patterns, then for all practical purposes of study and classification, we should consider it a planet. This perspective challenges the idea that formation history is the only thing that matters, suggesting that an object's present state and physical properties should carry significant weight. This naming debate is far more than simple academic semantics. It has real consequences for how we search for and understand these objects. If we classify all free-floating, planet-mass objects as brown dwarfs, we might be artificially inflating the population of failed stars in our galaxy while ignoring a potentially vast population of exiled worlds. Imagine a Jupiter-like planet that was violently flung out of its solar system during the chaotic early days of planetary formation. After billions of years of drifting alone, it cools down to the same temperature as a white dwarf that formed in isolation. To our telescopes, these two objects would appear identical. They would have the same mass, the same temperature, and similar atmospheric signatures. Yet, by the strict formation-based definition, one is a rogue planet and the other is a brown dwarf. This creates a profound classification problem. How do we tell them apart? The truth is, with our current technology, we often can't. This ambiguity forces astronomers to acknowledge that the clean categories we learned in school, star, brown dwarf, planet, are actually a spectrum, a continuum of celestial objects with messy, overlapping properties. The discovery of white dwarfs hasn't just added a new box to our cosmic checklist. It has forced us to tear down the old boxes and reconsider the entire filing system. It reminds us that nature does not always adhere to our human desire for neat and tidy labels, presenting us instead with fascinating hybrids that defy our simplest definitions. But if you want to understand the profound implications of these shadow worlds, you need to look no further than a single, specific object, a cosmic neighbor that has become the poster child for the entire Y-class. Its official designation is a mouthful, WISE 0855-0714, but its story is nothing short of spectacular. Discovered in data from the WISE telescope, this object instantly captured the astronomical community's attention for one simple reason. It is the coldest known object of its kind outside our solar system, a frozen sentinel drifting in the void a mere 7.2 light-years from Earth. To put that distance into perspective, only 3 star systems are closer to us than this solitary world. It is, for all intents and purposes, right on our cosmic doorstep, a hidden neighbor we never knew we had until just a few years ago. And its defining characteristic is its temperature, a value so mundane it becomes extraordinary in this context. WISE 0855 holds a temperature of around -10 degrees Fahrenheit, or about -23 degrees Celsius. That is colder than a winter night in Antarctica, and strikingly, it is a temperature commonly experienced here on Earth. The sheer normality of that number is what makes it so bizarre. We are accustomed to thinking of interstellar space as a place of extreme heat near stars and unimaginable cold in the shadows, but to find an object of planetary mass that is literally as cold as a terrestrial winter day redefines our sense of what's possible. This isn't a theoretical object in a distant nebula. This is a real, physical body with a climate you could almost relate to, existing in the emptiness just next door. The true revelation, however, came not just from measuring its temperature, but from peering into its atmosphere. Using the powerful Spitzer Space Telescope for follow-up observations, astronomers were able to analyze the faint infrared glow of WISE 0855 in greater detail. The data revealed an unmistakable chemical signature, the presence of water vapor, and even more significantly, strong evidence for clouds of water ice. Let that sink in for a moment. Here is a world without a sun, a solitary nomad drifting through the perpetual night of interstellar space. Yet, its atmosphere contains the same fundamental ingredient for life that dominates our own planet, and it has an active weather cycle involving that very substance. These aren't just trace amounts. The evidence suggests a thick, extensive layer of clouds, likely blanketing much of this frigid world. Imagine the scene, in the absolute darkness, with no sunrise or sunset to mark the passage of time. A blizzard of water ice crystals swirls endlessly through a deep, cold atmosphere. There is no surface for this snow to fall upon, no mountains to accumulate on. It simply exists in a perpetual state of suspension and circulation, a ghostly hydrological cycle playing out on a sunless scale. This discovery was a watershed moment because it proved that the atmospheric processes on these isolated worlds are not simple or static. They are dynamic and complex, capable of condensing volatile compounds and creating cloud structures in the most hostile of environments. The existence of water ice clouds on WISE 0855 provides a crucial bridge connecting this seemingly alien object to something much more familiar, our own solar system's gas giant, Jupiter. Jupiter's turbulent atmosphere is famously banded with clouds of ammonia ice, but deeper within its swirling layers, theoretical models have long predicted the existence of a separate deck of water ice clouds. We have never been able to directly observe these hidden water clouds on Jupiter, as they are buried too deep beneath the planet's thick upper atmosphere. WISE 0855, in a fascinating twist, acts as a natural laboratory for these very conditions. Because it is so much colder than Jupiter, the atmospheric layer where water can condense is shifted much higher up, making it accessible to our remote observations. In essence, by studying the water ice clouds in the atmosphere of this distant, cold neighbor, we are getting an unprecedented glimpse into the hidden weather systems of the giant planets in our own backyard. It's as if the universe has provided us with a dissected model of a gas giant, one where the inner workings are exposed for us to study. This transforms WISE 0855 from a mere curiosity into a vital key for understanding planetary atmospheres as a whole, demonstrating that the lessons learned from these dark, lonely worlds can illuminate the mysteries of the planets that orbit our own sun. This revolutionary capability is precisely what makes the James Webb Space Telescope our most powerful tool for illuminating these dark worlds. Think of previous telescopes like WISE and Spitzer as skilled scouts who could point into the darkness and whisper, "There's something out there." The James Webb Space Telescope, however, is the powerful searchlight we've finally switched on, capable of not just confirming the presence of these cosmic ghosts but studying their features in stunning detail. Its entire design philosophy is a direct answer to the challenge posed by objects like white dwarfs. Unlike the Hubble Space Telescope, which primarily observes invisible and ultraviolet light, JWST is a dedicated infrared observatory. It sees the universe in the exact kind of light these cold objects emit, the faint, long-wavelength glow of residual heat. To do this, it had to be placed in an orbit far from Earth's interfering warmth and equipped with a sun shield the size of a tennis court to keep its instruments at a cryogenically cold temperature, only a few degrees above absolute zero. This is because to detect the faintest whispers of heat from the cosmos, the telescope itself must be colder than the signal it is trying to measure. Its massive gold-coated mirror, spanning over 6.5 meters, acts as a colossal light bucket, gathering every precious photon of infrared light that has traveled for light years across space. This combination of size, cold, and technological precision gives JWST a sensitivity in the infrared spectrum that is 100 times greater than any previous telescope, transforming the faint thermal whispers of white dwarfs into clear, analyzable signals. With this unprecedented power, JWST is moving beyond mere detection and into the realm of true atmospheric science for these shadow worlds. One of its key instruments, the near-infrared spectrograph or NIRSpec, acts like a cosmic prism. It can take the gathered infrared light from a wide dwarf and split it into a detailed spectrum, a unique rainbow of sorts that is missing specific wavelengths. These missing lines are the fingerprints of molecules in the object's atmosphere, each one absorbing a very specific color of light. By reading this spectral barcode, astronomers can definitively identify which gases are present. We can move from theoretical predictions to concrete knowledge, confirming the existence of water vapor, methane, ammonia, and even more exotic compounds like hydrogen sulfide. But JWST goes even further than a simple ingredient list. The precise shape and depth of these absorption lines can reveal the atmospheric pressure at different altitudes, the temperature structure from the upper haze down into the deeper layers, and even hints of wind speeds. It can tell us if the atmosphere is clear or choked with global cloud decks, and by monitoring changes in the spectrum over time, it might even detect large-scale weather patterns, like the movement of vast storm systems or the formation and dissipation of those exotic salt and ice clouds. For the first time, we are not just seeing a dot of light, we are beginning to map the climate of a world that has never seen a sun. This profound new level of insight is already yielding results. JWST has turned its gaze towards known white dwarfs like our neighbor WISE 0855, and the data it is returning is nothing short of spectacular. Where Spitzer could only provide a few data points, JWST delivers a rich, high-resolution spectrum brimming with features that scientists can now interpret. Early analysis is confirming the widespread presence of those water ice clouds and is beginning to probe the complex chemistry of their formation. It is also searching for rarer molecules that could tell us about the object's history and internal processes. Is there evidence of phosphine, a gas that on Earth is associated with biological activity, but in these high-pressure, alien environments could be produced by purely geological means? Could we detect carbon monoxide, which would tell us about the atmospheric circulation patterns? Every new spectrum is a treasure trove of information, answering old questions while simultaneously posing thrilling new ones we never before had the precision to ask. JWST is effectively performing remote planetary science on worlds that have no star, treating these solitary nomads with the same detailed scrutiny we once reserved only for planets within our own solar system. It is a testament to human curiosity and engineering that we can now study the weather on a world light years away, a world so dark and cold it defies our basic definitions, and in doing so, we are rewriting the textbook on what constitutes a planet in our galaxy. Of course, the search for these cosmic ghosts extends far beyond a single telescope, creating a global collaboration across space and time that leverages every tool at our disposal. While WISE and JWST are the headline grabbers, they stand on the shoulders of other critical missions and are joined by powerful new allies. Take the Spitzer Space Telescope, for instance, which was retired in 2020. Spitzer was a pioneer in infrared astronomy, and its role in this hunt was not as a surveyor but as a specialist. For the coldest white dwarfs first spotted by WISE, like our neighbor WISE 0855, Spitzer provided the crucial follow-up observations. Its more sensitive infrared camera could dwell on these faint targets for much longer, gathering the additional data needed to refine their temperatures, confirm their distances, and even begin to probe their atmospheric composition. It was Spitzer that provided some of the strongest early evidence for those water ice clouds, transforming WISE's initial detection from a curious blip into a world we could begin to characterize. Spitzer acted as the expert witness, confirming the identity of the suspects that WISE had first pulled from a lineup of millions of stars. Looking ahead, the next great leap in this census of darkness will come from the Nancy Grace Roman Space Telescope, set to launch in the near future. Roman is not just an incremental improvement, it represents a paradigm shift in how we survey the sky. Imagine having a field of view over 200 times larger than the Hubble Space Telescope's infrared camera, but with the same incredible sharpness. This combination of a wide-angle lens and eagle-eye vision makes Roman perfectly suited to perform a deep, systematic, all-sky search for these faint, cold objects. While JWST is unparalleled in its ability to study individual white dwarfs in exquisite detail, its field of view is relatively small, like looking at the cosmos through a soda straw. Roman, by contrast, will throw open the windows, scanning vast swaths of the galaxy to find the most promising candidates for JWST to then investigate further. It's projected that Roman could discover hundreds of new white dwarfs, potentially tripling or quadrupling the known population, and giving us our first true statistical understanding of how common these dark worlds really are. This powerful synergy between observatories, with Roman as the prolific scout and JWST as the master analyst, will create a golden age for the study of these mysterious entities, moving us from studying a handful of peculiar examples to understanding them as a fundamental class of galactic object. And we must not forget the view from the ground. You might think that Earth's shimmering, turbulent atmosphere would make it impossible to spot such incredibly faint infrared objects, and for the most part you'd be right. But technology has found a way. Ground-based behemoths like the Keck Observatory in Hawaii and the Very Large Telescope in Chile employ a brilliant technology called adaptive optics. This system works by firing a powerful laser into the upper atmosphere to create an artificial guide star. Sensors then monitor how this laser beacon twinkles and distorts, and a computer uses that information to deform the telescope's mirror hundreds of times per second, actively cancelling out the atmospheric blurring in real time. The result is a view of the heavens that can sometimes rival the sharpness of the Hubble Space Telescope. This technology is what allows these ground-based giants to attempt direct imaging of the very brightest and closest white dwarfs. Their immense light-gathering power can be focused to not just detect the object, but to take spectra and monitor it for changes over time. While they can't compete with the infrared sensitivity of a cold, space-based telescope like JWST, they provide a vital complementary role, offering long-term monitoring campaigns that can track atmospheric weather patterns on these worlds over many years. This global network of eyes, both on the ground and in space, ensures that the hunt for shadow worlds is a continuous, multi-front effort, with each observatory playing to its unique strengths to slowly pull these cosmic phantoms out of the darkness and into the light of our understanding. So how do we pull detailed information about the chemical makeup of a distant, nearly invisible object? The answer lies in a technique as fundamental to astronomy as the telescope itself, a method called spectroscopy. At its heart, spectroscopy is the science of reading light, but not just its brightness or color. It's about dissecting light into its most fundamental components to uncover the hidden stories it carries across the light years. Every object in the universe that emits or reflects light leaves a unique signature within that light, a kind of cosmic barcode. For a blazing star, that barcode tells us about its temperature and the elements fusing in its core. For an ultra-cool white dwarf, the faint infrared glow it emits holds the specific chemical fingerprints of the gases swirling in its atmosphere. It's the only way we can go from knowing that a dark world exists to understanding what it is made of. To grasp how this works, think about what happens when you pass sunlight through a glass prism. The white light spreads out into the familiar colors of the rainbow: red, orange, yellow, green, blue, indigo, and violet. This band of colors is called a spectrum. Now, if you were to look at the sun's spectrum in exquisite detail, you would notice that it's not a perfectly smooth, continuous gradient. It's actually punctuated by hundreds of fine, dark lines, like missing slivers of color. These aren't flaws or errors, they are vital clues. These dark lines are created by different elements in the sun's outer atmosphere, such as hydrogen, helium, and sodium. Each element absorbs light at a very specific set of wavelengths, effectively plucking those specific colors out of the broader rainbow. every single element and molecule in the universe has its own unique pattern of absorption lines, a fingerprint as distinct as a human's. Sodium always absorbs the same shades of yellow, hydrogen always absorbs specific reds and blues, and so on. By matching the pattern of dark lines we observe in a star's spectrum to the patterns we've measured in laboratories here on Earth, we can say with certainty exactly which chemicals are present in that star, all from millions or even billions of light years away. This same principle applies perfectly to the cold, dark white dwarfs, just in a different part of the light spectrum. Since these objects are virtually invisible in optical light, astronomers instead capture their faint infrared glow. The light from a white dwarf starts deep within its warm interior and tries to escape outward through its atmosphere. As it passes through the layers of swirling gases, molecules in that atmosphere act like selective filters. Water vapor, methane, and ammonia are particularly greedy, absorbing very specific wavelengths of infrared light. So, by the time this faint thermal radiation finally escapes into space and travels across the vast distance to our telescopes, it is imprinted with the unique absorption pattern of every molecule it encountered. A spectrograph on a telescope like JWST acts as an ultra-precise infrared prism, splitting that faint light into a detailed spectrum. What astronomers then see is not a simple rainbow, but a jagged line graph full of dips and valleys. Each dip corresponds to a specific wavelength of infrared light that was absorbed by a specific molecule. A deep dip at one particular wavelength is the unmistakable calling card of water vapor. A cluster of dips at another set of wavelengths screams the presence of methane. It's a direct chemical readout of the atmosphere's composition, allowing us to literally read the atmospheric recipe of a world we will never physically visit. The power of this technique goes far beyond just creating a simple ingredient list, however. The depth and shape of these absorption lines reveal a wealth of information about the physical conditions in the atmosphere itself. A very deep, broad absorption line suggests there is a large amount of that molecule present, and that it exists in a dense, high-pressure region of the atmosphere. A sharper, narrower line might indicate the gas is found in a thinner, upper layer. Furthermore, the precise position of the lines can be shifted slightly by motion. If the atmosphere on one side of the white dwarf is rotating toward us, the absorption lines will shift very slightly toward the blue end of the spectrum. If the other side is rotating away, the lines shift toward the red. By carefully measuring this subtle Doppler shift, scientists can actually calculate how fast these solitary worlds are spinning, determining the length of their day even though they have no solid surface to observe. Spectroscopy transforms that single, faint point of infrared light into a dynamic, three-dimensional map of atmospheric chemistry, structure, and motion, giving us a profound and intimate understanding of these cosmic ghosts from an unimaginable distance. Given their profound darkness and cold, you might assume these white dwarfs are completely inert, frozen balls of gas simply adrift, but that couldn't be further from the truth. Deep within their cores, a silent, slow-burning fire provides the faint warmth that makes them detectable at all. This isn't the raging nuclear furnace of a star, but something far more subtle, the lingering remnant of their own violent birth. Every white dwarf begins its life in a gravitational collapse as a cloud of gas and dust contracts under its own weight. This process converts an immense amount of gravitational potential energy into thermal energy, heating the nascent object to incredible temperatures. For the briefest cosmic moment, the very center of a newborn white dwarf might even be hot enough to spark a special, limited kind of nuclear fusion. But this fire is fleeting. Unlike a true star, which can sustain hydrogen fusion for billions of years, a brown dwarf lacks the mass to maintain the core pressure and temperature needed for that ongoing reaction. What we detect as heat from an older white dwarf, then, is not the product of active fusion, but simply this primordial formation heat, trapped deep within its atmosphere, very, very slowly leaking out into the frigid vacuum of space. The rate of this cooling process is one of the key factors that determines a white dwarf's place on the temperature spectrum. Think of it like a freshly baked cake pulled from the oven. At first, it's very hot, radiating a lot of infrared energy. This would be analogous to a warmer L or T dwarf, but as it sits on the counter, it cools down. After a few hours, it's merely warm to the touch, and after a full day, it reaches room temperature. A white dwarf is the cosmic equivalent of that cake a day later. It has shed most of its initial heat but still retains a faint internal warmth. The larger the object, the more heat it can trap and the longer this cooling takes. A more massive white dwarf has a stronger gravitational pull, which compresses its core more tightly, providing better insulation against heat loss. This means that when we discover a relatively warm white dwarf with a temperature of, say, a few hundred degrees, we might be looking at a fairly young and massive object, one that is still in the early stages of its multi-billion-year journey toward absolute cold. Conversely, the very coldest white dwarfs, like WISE 0855, are likely among the oldest and least massive of their kind, objects that have been radiating away their birthright heat for most of the age of the universe and are now in their final stages of cosmic retirement. Now, for the very most massive white dwarfs, there is a potential for one last faint whisper of nuclear activity. This revolves not around common hydrogen, but a much rarer isotope called deuterium, sometimes known as heavy hydrogen, because its nucleus contains both a proton and a neutron. The barrier to igniting deuterium fusion is significantly lower than that for standard hydrogen. An object only needs about 13 times the mass of Jupiter to reach the core temperatures necessary, around 1 million degrees Kelvin, to begin fusing deuterium nuclei together. This process can provide a small supplemental heat source for a relatively short period, perhaps a mere 100 million years, which is just a blink in cosmic time. So, the very most massive and youngest white dwarfs might have this faint deuterium fusion flickering in their cores, a final, sputtering gasp of stellar ambition before the fire goes out for good. However, for the vast majority of white dwarfs we are discovering, especially the colder ones, even this modest fusion reaction has long since ceased. Their glow is purely the legacy of that initial gravitational collapse, a dying ember in the eternal night. This leads to a fascinating question. What is the actual internal structure of one of these objects? What is it like deep beneath those layers of water ice and ammonia clouds? The answer involves states of matter that are utterly alien to our everyday experience. As you journey inward from the tenuous outer atmosphere, the pressure increases exponentially due to the immense weight of the overlying gases. Eventually, the hydrogen gas that makes up the bulk of the white dwarf becomes so compressed that it undergoes a dramatic transformation. It ceases to behave like a familiar gas and enters a state known as a dense fluid, a strange, soup-like phase where the distinction between a gas and a liquid blurs away. This fluid molecular hydrogen extends deep into the interior, acting as a vast global ocean with no surface or floor. At even greater depths, the pressure becomes so astronomical, millions of times greater than the pressure at the bottom of Earth's ocean, that another profound change occurs. The electrons are literally squeezed right off their parent hydrogen atoms, creating a swirling sea of free electrons and naked protons. This is a state known as a degenerate electron gas. The behavior of this degenerate matter is governed by the bizarre laws of quantum mechanics, not the classical physics we're used to. In this state, the electrons resist being packed any closer together with a powerful outward pressure, a force that has nothing to do with heat or thermal expansion. It is this electron degeneracy pressure, not fusion, that primarily supports a white dwarf against the relentless crush of its own gravity, preventing it from collapsing further. This makes the core of a white dwarf a deeply strange place, a super-dense metallic fluid of hydrogen supported by quantum mechanical effects, slowly conducting the remnant heat of formation outward over billions of years. It is a far cry from the molten iron-nickel core of Earth or the churning metallic hydrogen dynamo of Jupiter. It is a unique and exotic interior, a testament to the incredible variety of physical states that matter can assume in the cosmos. Now, if this entire journey into the nature of white dwarfs feels like we're discussing a handful of rare cosmic curiosities, prepare for a perspective shift that redefines our entire galactic neighborhood. The emerging picture from theoretical models and indirect observations suggests these shadow worlds are not rare anomalies at all. In fact, they could be one of the most common types of objects in the entire Milky Way, with some estimates boldly proposing they might even outnumber all the stars in our galaxy. Just let that sink in for a moment. We look up and see a sky filled with points of light, but for every single one of those stars, there could be one, two, or even more of these dark, planet-like bodies drifting unseen in the vast spaces between them. Our galaxy, which we often visualize as a brilliant spiral of starlight, could be equally defined by a hidden, dark population of cold, solitary worlds, a ghostly infrastructure woven throughout the luminous arms. Understanding how we can possibly estimate the population of objects we can't directly see requires a bit of cosmic detective work. Since conducting a straightforward census is impossible, astronomers rely on a powerful combination of statistical extrapolation and the subtle effects of gravity. The process often starts with the small sample we have found. Telescopes like WISE and the upcoming Roman Space Telescope survey specific deep fields of the sky. When they discover a few white dwarfs in that carefully studied patch, scientists can use that number to extrapolate an estimate for the entire galaxy. It's similar to a biologist estimating the number of fish in a lake by catching, tagging, and releasing a few from one small area, and then making a calculated guess about the total population. Of course, this method has significant uncertainty. We have to make assumptions about how uniformly these objects are distributed, and our current searches are still limited by sensitivity, meaning we're only seeing the very brightest and closest of these incredibly faint objects. But even with these limitations, the initial numbers are startling, consistently pointing toward a vast, unseen multitude. The most compelling indirect evidence for this hidden population, however, comes from a fascinating phenomenon known as gravitational microlensing. This effect is one of the most elegant predictions of Einstein's theory of general relativity. It works like this: when a massive object like a white dwarf passes almost directly between us and a distant background star, its gravitational field acts like a tiny lens in space. It bends and focuses the light from that faraway star, causing it to temporarily brighten in a very specific way. For a few hours or days, the background star appears to flare up before fading back to its normal brightness as the lensing object moves out of alignment. The beauty of this method is that it doesn't rely on the lensing object emitting any light at all. It works purely through the warping of spacetime by mass. A perfectly dark, cold white dwarf would create a microlensing event just as easily as a bright star. Over the past few decades, large-scale microlensing surveys have been monitoring millions of stars in the direction of the galactic bulge, looking for these telltale flashes. And they have found them, thousands of them. While many of these events are caused by known types of stars, a significant fraction of the lenses remain unidentified. Crucially, the characteristics of these unseen lenses, their inferred mass, and the fact that they are not detected by any other means, strongly suggest they are low-mass, isolated objects. Many astronomers argue that the simplest explanation for a large number of these mysterious lenses is a vast population of free-floating planetary mass objects, a category that includes the coldest white dwarfs. The microlensing data doesn't just hint at a few stray worlds. It suggests a galaxy teeming with them, with numbers potentially reaching into the hundreds of billions. This gravitational evidence paints a picture of a Milky Way where the dark, interstellar spaces are not empty at all, but are instead a dynamic environment populated by a countless fleet of nomadic worlds, forever untethered from the light of any sun. This potential abundance forces us to reconsider the very narrative of planetary formation. Where did all these dark worlds come from? There are two leading theories, and both likely contribute to this hidden population. The first is the traditional brown dwarf formation model, where these objects collapse directly from isolated clouds of gas and dust, just like stars but on a smaller scale. The second, and perhaps more prolific, source is planetary ejection. In the chaotic early days of a solar system, gravitational interactions between young, massive planets can be violent. A close encounter with a Jupiter-sized sibling can easily sling a planet out of its orbit, hurling it into the interstellar void at high speed. Simulations of planetary system formation show that this is not a rare event, it might be a common outcome. Our own solar system may have ejected several giant planets in its youth. These exiled worlds would then drift alone, cooling over billions of years until they become indistinguishable from a white dwarf that formed in isolation. If ejection is this common, then the galaxy's population of dark, free-floating planets could be a direct relic of the turbulent birth of countless solar systems, a cosmic diaspora of worlds that never found a home. This brings us to a truly compelling and slightly haunting possibility. What if the majority of these dark worlds aren't failed stars at all, but are instead cosmic orphans planets that were violently thrown out of their home solar systems and now drift alone in the perpetual night? This idea, known as the rogue planet hypothesis, suggests that a significant fraction of the white dwarfs we are detecting are actually exiled giants, Jupiters that were banished from their stellar families. To understand how this could happen, we need to rewind the cosmic clock to the very beginning of a solar system's life. When a star is young, it is surrounded by a swirling, chaotic disk of gas and dust where planets are beginning to coalesce. In these early days, the system is a gravitational free-for-all. Dozens of planetary embryos and young gas giants are all vying for stable orbits, and their interactions are anything but peaceful. It's a celestial game of billiards on an epic scale. In such a crowded environment, close encounters are inevitable. When two massive planets pass near each other, their gravitational pull can slingshot one of them inward and the other outward with such immense velocity that it completely escapes the star's gravitational grasp. This ejected planet is then cast adrift, becoming a permanent nomad of the interstellar void. Computer simulations of planetary system formation show that this isn't a rare, freak occurrence. It may be an extremely common, almost expected part of the planet-building process. Some models suggest that for every solar system that settles into a stable configuration like our own, it may have ejected one or even several of its original giant planets during its tumultuous youth. Our own solar system might be the unusually calm exception, not the rule. If that's the case, then the galaxy could be filled with the ghosts of these lost worlds, a vast population of orphans that outnumbers the stars themselves. This theory of planetary ejection has profound implications, not just for counting worlds, but for the very potential of life in the universe. When we think about life as we know it, we instinctively look to the habitable zone, that narrow orbital band around a star where temperatures are just right for liquid water to exist on a planet's surface. A world like Earth, basking in the steady warmth of our sun, seems like the perfect cosmic cradle. But a rogue white dwarf, by its very nature, exists in the ultimate anti-habitable zone. It has no star, it is a world of absolute darkness and profound cold, its surface temperature dictated only by the faint, dwindling ember of its internal heat. Without a source of external energy, the possibility for life as we understand it seems to vanish. There would be no photosynthesis, no day-night cycle, no seasons. The very chemistry that drives biological processes on Earth would grind to a near halt in the deep freeze of interstellar space. The surface, or more accurately, the upper atmosphere where pressures are Earth-like, would be an environment of extreme austerity. Any hypothetical organism would have to survive on a trickle of geothermal energy radiating from the planet's interior, a resource that fades away over billions of years as the world continues to cool. While we have discovered extraordinary extremophiles on Earth thriving near volcanic vents on the dark ocean floor, those ecosystems are ultimately powered by the Earth's internal heat, which itself is supplemented by the radioactive decay of elements created in long-dead stars. A lone rogue planet's energy budget is far, far smaller, making even these dark, chemosynthetic ecosystems seem energy-rich by comparison. However, before we completely write off these dark worlds as sterile wastelands, we must confront a fascinating and counterintuitive idea. What if a rogue planet could provide its own warmth, creating a sheltered oasis in the void, completely independent of any star? This concept hinges on two potential heat sources: the planet's residual formation heat and the curious effects of tidal forces. First, let's consider the internal heat. A large, young rogue planet, freshly ejected from its system, would still be remarkably warm inside. This geothermal energy could, in theory, sustain a vast global ocean of liquid water deep beneath a thick, protective crust of ice. We see a similar phenomenon in our own solar system on moons like Europa and Enceladus, which are far from the sun's warmth but are kept liquid internally by the gravitational tug of war with their host planet. A rogue planet would have no such external tidal forces, but its own substantial internal heat could be enough to maintain a subsurface ocean for billions of years, especially if it was massive and possessed a rocky core rich in radioactive elements. Within such a buried ocean, shielded from the harsh radiation and absolute zero temperatures of space by kilometers of ice, the conditions for life might just be possible. It would be a life utterly isolated, thriving in eternal darkness, unaware that a universe of stars even exists outside its icy shell. The second, more speculative source of heat involves an even more exotic scenario: a rogue planet with a large, warm moon. If a gas giant is ejected from its solar system, it's plausible that it could take its entire lunar system along with it. In this setup, the gravitational interaction between the planet and its moon, the constant rhythmic flexing of their interiors, could generate significant tidal heating. This is the same process that keeps the interior of Jupiter's moon Io molten and volcanically active. In the cold of interstellar space, this tidal energy could be the sole source of warmth for a system untethered from any star. The moon, heated from within, could potentially maintain a subsurface ocean, or even, if it was massive enough, a thick atmosphere that traps the tidal heat at its surface. Imagine a lone, Earth-sized moon orbiting a Jupiter-sized rogue planet with a surface warmed not by sunlight, but by the constant gravitational kneading from its planetary partner. Its sky would be dominated by the colossal, banded globe of its gas giant parent, with the background of stars providing the only other source of light. It's a breathtaking and profoundly lonely picture, a single, life-bearing oasis adrift in the unimaginable vastness between the stars. While this remains firmly in the realm of speculation, it forces us to expand our definition of a habitable environment and reminds us that life, if it exists out there, may have found ways to thrive in the most unexpected and dark corners of the galaxy. Ultimately, the question of whether a white dwarf is a failed star or a rogue planet is more than just a semantic debate. It forces a fundamental shift in our cosmic perspective. If the rogue planet theory is correct, then the standard picture of a galaxy filled with solar systems, each with planets neatly orbiting a central star, is incomplete. It suggests a dual architecture to the Milky Way. There is the luminous, star-centered universe we are familiar with, And then there is a dark, parallel universe of solitary worlds, a ghostly population that may be just as numerous, if not more so. These two populations would interact only through the faint pull of gravity or the rare, momentary flash of a microlensing event. This realization profoundly impacts the search for life. Our current strategies focus almost exclusively on planets orbiting stars, monitoring their atmospheres for biosignatures as they pass in front of their sun's light. But if a vast number of potentially habitable environments are actually these free-floating worlds, huddling for warmth around their own internal heat or tidal energy, then we have been looking for life in only one of its possible homes. A galactic census that only counts worlds with stars is missing a potentially enormous chapter of the story. The silent, dark white dwarfs drifting in the void may be more than just celestial curiosities. They could represent an entirely separate, hidden realm of astronomical possibility, a testament to the galaxy's turbulent past and its astonishing hidden diversity. But to truly grasp the alien nature of these worlds, we must venture beyond their chemical composition and into the heart of their dynamic systems, their weather. The climate of a white dwarf is a study in extremes, driven not by the gentle gradients of a sunlit day, but by the stark divide between a faint internal warmth and the absolute cold of space. This creates an engine for meteorology that is both violent and strangely familiar. The primary driver is heat redistribution. Deep within the atmosphere, pockets of warmer gas, buoyed by their own heat, rise in colossal convection currents. As they ascend, they expand and cool, causing the exotic chemicals within them to condense into global decks of clouds. Then, having released their heat to the void, the now colder, denser air plunges back into the depths in a furious downdraft. This unending cycle generates winds of unimaginable ferocity. We are not talking about terrestrial hurricanes, but planet-spanning jet streams that could easily reach speeds of hundreds, if not thousands, of miles per hour, scouring the atmosphere and sculpting the cloud formations into vast, swirling bands and massive, long-lived storm systems reminiscent of Jupiter's Great Red Spot, but playing out in perpetual darkness. The cloudscapes themselves are where the chemistry becomes a breathtaking spectacle, forming a layered atmosphere of almost incomprehensible variety. At the very highest, coldest altitudes, where the thin haze meets the interstellar vacuum, you might find a wispy layer of clouds made not of water, but of ammonia ice crystals, casting a pale, yellowish veil over the world below. Descending through this layer, the temperature might become just right for water vapor to condense, creating a dense, global deck of water ice clouds. This is the realm of the eternal blizzard, where flakes of ice, made not from evaporated oceans but from the planet's primordial water supply, swirl in the hyper-fast winds, never finding a surface to land upon. But the true strangeness emerges as we journey deeper into the warmer, higher-pressure layers closer to the internal heat source. Here, the temperature can soar to levels that would melt lead. In these torrid zones, the condensing materials are no longer ices, but minerals and metals. Theoretical models suggest that in the atmospheres of slightly warmer white dwarfs, you could find clouds composed of liquid droplets of iron and silicates, raining a scorching downpour of molten metal. On others, the clouds might be made of common salt sodium chloride, or even a fine dust of sand-like particles, such as in statite or corundum. Imagine a storm where, instead of water, the sky rains hot, liquid iron or a blizzard of fine, abrasive sand driven by supersonic winds. This is the bizarre precipitation of a white dwarf, a world where the very definition of weather is rewritten. The behavior of these exotic clouds adds another layer of complexity. Just as on Earth, where different cloud types form at different altitudes, a white dwarf's atmosphere can host multiple distinct cloud layers simultaneously. A single atmospheric column might have a high-altitude haze of ammonia, a mid-level deck of water ice, and a deep, churning layer of molten salt or silicate droplets below. The interactions between these layers could create weather patterns of stunning intricacy. A powerful updraft from the deep interior might inject hot, vaporized minerals into the colder upper atmosphere, where they would rapidly condense and fall back down, creating a violent storm of hot sand or salt. The different cloud decks, composed of materials with different colors and reflective properties, could create a banded appearance to the atmosphere, with dark belts where the clouds are thin, revealing the hotter depths below, and bright zones where the thick, reflective cloud decks dominate. Observing how these bands shift and change over time could allow us to map the wind patterns and storm systems on a world that has never seen a sunrise, turning a single point of infrared light into a dynamic global weather map of an alien world. And so we arrive at the million-dollar question, the one that tugs at our imagination whenever we discover a new world, no matter how hostile it may seem. Could these dark, cold, white dwarfs possibly host life? It's a query that pits our hopeful search for cosmic companions against the brutal, unyielding laws of physics, and the initial assessment is, to put it mildly, bleak. Let's first consider the three fundamental pillars of life as we know it: a source of energy, a solvent for chemical reactions like liquid water, and a stable environment. A white dwarf seems to systematically dismantle each one. The most obvious obstacle is the complete and utter lack of sunlight. Photosynthesis, the engine that powers virtually every ecosystem on Earth's surface, is impossible here. There is no day, no growing season, no harvest of stellar energy. This forces any hypothetical organism to rely on chemical or geothermal energy, a far less abundant and efficient power source. Next, consider the temperatures. While the upper atmospheres of some white dwarfs can be surprisingly temperate, even Earth-like, this is a cruel illusion. The atmospheric pressure at those altitudes is a tiny fraction of what we experience at sea level, an almost perfect vacuum where liquid water cannot exist. It would instantly flash freeze or boil away. To find pressures high enough for liquid water, you would need to descend deep into the atmosphere, into the soupy, dense layers. But there, you encounter the third and perhaps most crushing problem. The cold gives way to a scalding heat, and the pressure itself becomes astronomical, enough to crush any complex molecular structure we can envision. It appears to be a classic cosmic catch-22. The places with the right pressure are lethally hot and crushingly dense, while the places with the right temperature are a near vacuum. On the surface of this evidence, the idea of life on a white dwarf seems not just unlikely, but fundamentally impossible. However, before we completely close the book, we must look to our own planet for a lesson in biological stubbornness. Here on Earth, life has flourished in places we once deemed uninhabitable, in the scalding, acidic hot springs of Yellowstone, in the radioactive waters of nuclear reactors, and most tellingly, in the eternal darkness at the bottom of the ocean. Clustered around hydrothermal vents, entire ecosystems thrive completely independent of the sun. They are powered by chemosynthesis, a process where microbes convert the chemicals spewing from the Earth's interior, like hydrogen sulfide, into usable energy. This is a paradigm-shifting concept. Life does not require a star, it only requires a consistent energy gradient and the right chemistry. So, could a similar process unfold in the atmosphere of a white dwarf? It's a staggering long shot, but the theoretical pathway exists. The turbulent atmosphere of a white dwarf is a vast chemical reactor, filled with a rich soup of molecules like methane, ammonia, and hydrogen. A floating, microbial-like life form could, in theory, evolve to harvest energy from the chemical reactions between these gases, perhaps using ultraviolet radiation from distant stars or even internal thermal energy as a catalyst. These hypothetical organisms wouldn't live on a surface. They would be permanent aerial plankton, drifting in the dense atmospheric layers where temperatures and pressures might, just for a moment, align in a habitable window. They would need to be incredibly resilient, capable of withstanding violent winds and potentially corrosive chemicals. But the precedent set by Earth's extremophiles tells us we should never underestimate life's ingenuity. Yet, even this speculative scenario runs into another profound challenge, the question of stability and complexity. The ecosystems around Earth's hydrothermal vents are stable for centuries, anchored to a specific, energy-rich location on the seafloor. The atmosphere of a white dwarf, by contrast, is a maelstrom of churning gases and ferocious winds. Any delicate chemical process that could lead to the formation of complex molecules would be constantly disrupted. Furthermore, for life to evolve beyond the most basic single-celled stage, it needs a stable environment over geological timescales. It needs a place where offspring can reliably find the same conditions as their parents, a continuity that allows for slow, gradual adaptation. The violently convective and turbulent nature of a white dwarf's weather makes it incredibly difficult to imagine such a stable niche existing for billions of years. The energy gradients would be shifting, the chemical soups diluting and reforming, and any nascent, complex molecule would be torn apart or swept away long before it could replicate and evolve. So, while the raw chemical ingredients and an energy source might theoretically be present, the chaotic and transient nature of the environment itself may be the ultimate deal-breaker, preventing the delicate dance of chemistry from ever progressing into the symphony of biology. The path to life is not just about having the right parts, it's about having a quiet, stable workshop in which to assemble them, and that may be the one luxury a white dwarf's stormy atmosphere cannot provide. This curious cosmic scarcity leads us directly to one of the most perplexing mysteries in modern astronomy, a phenomenon known as the brown dwarf desert. For decades, as our planet hunting techniques improved, astronomers began to notice a startling and consistent pattern around stars similar to our Sun. While we found plenty of planets, both small and large, and we found plenty of distant stellar companions, there was a glaring absence of objects in between. There seemed to be a desert, a vast, barren region devoid of close-orbiting brown dwarfs. These failed stars, including the warmer L and T classes, and by extension the cold white dwarfs, are remarkably rare as immediate companions to Sun-like stars. It's as if nature has a specific aversion to placing these particular objects in tight orbits around solar-type stars. You can find plenty of planets within that orbital space, and you can find plenty of stars, but the brown dwarfs are the missing piece, the cosmic outliers that refuse to settle down in this particular neighborhood. This isn't just a small statistical fluke. The desert is a robust and well-documented feature of our galactic landscape. It tells us that our theories of how star systems form were missing a crucial piece of the puzzle, and the existence of white dwarfs, especially the free-floating ones, might just hold the key to understanding why this desert exists in the first place. So, why would there be such a pronounced gap? Why is it so difficult for a brown dwarf to exist as a close companion to a star like our own? Astronomers have developed several compelling theories, and they all point toward a violent and dynamic process during the earliest stages of a solar system's life. The first theory revolves around the very mechanism of formation itself. Stars and their planets are born from a single, collapsing cloud of gas and dust called a nebula. As this cloud spins and flattens into a disk, the vast majority of the material falls inward to form the central protostar. But sometimes, if the disk is massive and turbulent enough, a second clump of gas can collapse directly within the disk itself, potentially forming a brown dwarf companion. However, there's a problem with this scenario in the close-in regions. The intense gravitational pull of the newborn star makes it incredibly difficult for a second substantial object to coalesce so nearby. The process is inherently competitive, and the star almost always wins, hoarding the vast majority of the material for itself and starving any potential brown dwarf sibling before it can fully form. It's like trying to build a sandcastle right at the water's edge as the tide is coming in. The waves from the much larger star simply disrupt the process, preventing a stable structure from ever taking hold. This leads to the second and perhaps more dramatic explanation: gravitational ejection. Imagine the early solar system not as a calm, orderly place, but as a chaotic gravitational arena filled with dozens of young, massive planetary bodies all vying for a stable orbit. In this cosmic free-for-all, close encounters are not just possible, they are inevitable. Now, consider what happens when a developing brown dwarf, an object with dozens of times the mass of Jupiter, interacts with a true star. Their gravitational dance can become extremely unstable. A close pass can act like a gravitational slingshot, flinging the smaller, less massive brown dwarf clear out of the system entirely, sending it on a one-way trip into the interstellar void. This theory is particularly compelling because it creates a direct link between the brown dwarf desert we observe around Sun-like stars and the population of free-floating white dwarfs we are discovering with telescopes like WISE and JWST. The solitary white dwarfs drifting in the darkness might not all be lonely from birth. Many could be the exiled survivors of these ancient gravitational battles, ejected from their home systems and now condemned to an eternity of cold, solitary travel. The desert, in this view, isn't empty because nothing formed there. It's empty because the objects that did form there were violently evicted, their former homes now showing no trace of the tumultuous past. This is where the detailed study of white dwarfs becomes absolutely critical to solving the puzzle. By carefully measuring the properties of these free-floating objects, their masses, their atmospheric compositions, and their ages, we can look for forensic evidence of their origins. For instance, if a large proportion of white dwarfs have chemical signatures that suggest they formed in the rich disk of a star, rather than from an isolated gas cloud, it would provide powerful support for the ejection theory. Elements and isotopes locked in their atmospheres could act as a birth certificate, telling us about the environment in which they were born. Furthermore, by getting a better statistical handle on just how many of these solitary white dwarfs exist in our galactic neighborhood, we can compare that number to the predicted number of ejections from planetary formation models. If the numbers match, it would be a strong indication that the desert was indeed cleared out by a process of cosmic banishment. Every new white dwarf that telescopes like JWST and the upcoming Roman Space Telescope discover and characterize adds another data point to this grand investigation. They are not just mysterious worlds in their own right. They are living fossils, holding within their faint glow the secrets of a violent, formative era that shaped countless solar systems, including potentially our own. Understanding their history helps us complete the story of how star systems are built and why ours looks the way it does today, seemingly free of a close-in brown dwarf companion. Given that we are now finding white dwarfs with temperatures comparable to a chilly autumn day on Earth, it's natural to wonder if this is truly the end of the line. Could there be objects out there even colder and darker than the current Y-class, pushing the boundaries of what we consider a detectable world? The short answer is a resounding yes, and it leads us to the fascinating frontier of hypothetical classifications. Some astronomers have already begun to speculate about what might lie beyond Y, perhaps designating the next category as the Z-class. This wouldn't just be an arbitrary label. It would represent a population of objects that have cooled so dramatically they have nearly reached thermal equilibrium with the cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space at a frigid -454 degrees Fahrenheit. These would be the ultimate cosmic ghosts, objects whose internal heat has faded to almost nothing, leaving them just a few degrees above the absolute zero of space itself. So, what is the physical limit to how cold a free-floating object can become? The cooling process for a brown dwarf or a rogue planet is a one-way journey. After its formation, heat is radiated away over trillions of years. the object's temperature will asymptotically approach the temperature of the surrounding environment, the cosmic background radiation. Reaching this point would be the final state of cosmic retirement. An object at this stage would be virtually impossible to detect through its thermal emissions alone, as it would be indistinguishable from the cold backdrop of the universe. Its only remaining signature on the cosmos would be through the subtlest of gravitational influences, perhaps through microlensing or by its faint gravitational pull on the fabric of space-time itself. The search for these ultimate dark worlds is therefore a race against the limits of physics and technology, pushing our telescopes to detect the faintest possible whispers of warmth against the coldest possible background. This pursuit is actively shaping the next generation of astronomical surveys. The upcoming Nancy Grace Roman Space Telescope, with its immense wide-field vision, is expected to uncover hundreds more white dwarfs, and among them, it may very well find the first candidates for this new colder class. These objects would be the oldest of the old, having drifted for so long that their primordial fires have all but gone out. Confirming their status, however, would fall to the James Webb Space Telescope or its successors, which would need to perform painstakingly long observations to gather enough of their infinitesimal infrared glow to prove they have crossed the threshold from Y into a new realm of cold. Discovering a Z-class object wouldn't just add another page to our cosmic catalog. It would complete our understanding of the entire life cycle of substellar objects, from their fiery beginnings to their final, silent state as near-perfect black bodies in the eternal night. It represents the final frontier in the hunt for the dark, hidden architecture of our galaxy. So given that these white dwarfs are cloaked in near-total darkness, how do we actually take a picture of one? This is where the field of astronomy pushes its technology to the absolute brink, employing techniques of such precision and cleverness that they border on the magical. The method is known as direct imaging, and the goal is as simple as it is daunting: to isolate the infinitesimally faint point of light from a white dwarf and separate it from the overwhelming blackness of space and the glare of nearby stars. It's the astronomical equivalent of trying to photograph a single firefly hovering right next to a giant, brilliant searchlight from miles away. The primary weapon in this fight is an ingenious device called a coronagraph. Originally invented to study the sun's faint outer atmosphere, the corona, by blocking out the blinding solar disk, the coronagraph has been adapted into an essential tool for hunting the darkest objects in the universe. Inside a powerful telescope, the coronagraph is a small, precisely engineered mask that physically blocks the intense light from a star, creating an artificial eclipse right within the instrument itself. By doing so, it reveals the much fainter objects lurking in the star's immediate vicinity. For white dwarfs that happen to have a distant stellar companion, the coronagraph can block that star's glare, allowing the faint thermal glow of the brown dwarf to finally be seen. But for the solitary white dwarfs, the ones drifting completely alone, the challenge is even greater. There's no star to block. There's only an unbelievably dim speck of infrared light that must be distinguished from the random noise of the universe itself. The raw image that comes from the telescope is never a clean, crisp picture. It's a grainy, murky sea of digital static filled with artifacts from the camera's detectors, faint glows from zodiacal dust in our own solar system, and the indistinguishable light of countless distant galaxies. Buried within this chaotic mess is the signal from the white dwarf, a signal so weak it might comprise only a handful of photons collected over hours of continuous observation. Isolating this signal requires a digital excavation project of incredible sophistication. Astronomers use advanced processing algorithms, often based on a technique called angular differential imaging. Here's how it works. As the telescope tracks its target, the entire instrument slowly rotates throughout the night. This causes the faint light from the actual celestial object to stay fixed in position relative to the stars, while the noisy artifacts and glints within the telescope's own optics rotate along with the instrument. By taking hundreds of images and then using complex software to meticulously subtract everything that moves, scientists can slowly, painstakingly uncover the static point of light that is their target. It's a statistical and computational marvel, a process of averaging away the chaos until the truth of the signal emerges. The resulting image is often less of a detailed photograph and more of a confirmed detection, a small, pixelated blip that, after all that effort, is proven to be a real world and not just a flaw in the data. Some of the most heroic successes in this endeavor have come from the world's largest ground-based observatories, like the Keck telescopes in Hawaii and the Very Large Telescope in Chile, equipped with their adaptive optics systems and powerful coronagraphs. One of the best direct images we have is of a white dwarf known as WISE 0855, that same frigid neighbor we've discussed before. The image is not what you'd see in a sci-fi movie. It's a single, bright pixel, or perhaps a small cluster of pixels glowing against a dark, digitally clean background. But to an astronomer, that pixel is a universe of information. It confirms the object's position, allows for precise measurements of its brightness in different infrared colors, and verifies that it is indeed a single, point-like source and not a distant galaxy masquerading as something closer. Each one of these direct images is a monumental achievement, the culmination of years of telescope design, nights of perfect atmospheric conditions, and countless hours of supercomputer processing time. They are our proof, our tangible evidence that these cosmic ghosts are not just theoretical constructs inferred from data, but real, physical bodies that we can point to and say, there it is. They are the final, crucial step in transforming these shadow worlds from spectral whispers in a data stream into actual places in our galaxy. Perhaps the most empowering aspect of this cosmic ghost hunt is that you don't need a doctorate in astrophysics or access to a billion-dollar space telescope to contribute to the search. The discovery of these elusive worlds is, in many ways, a collaborative effort that stretches far beyond professional observatories and into the homes of curious people all around the globe. This is the world of citizen science, a movement where public volunteers partner with researchers to tackle massive datasets that would be impossible for any small team of scientists to analyze alone. The challenge with finding white dwarfs, especially in the vast infrared sky surveys from telescopes like WISE, is that computers are excellent at processing immense volumes of data, but they can still struggle with the nuanced task of pattern recognition. They can be fooled by image artifacts, the faint glow of distant galaxies, or the trails of asteroids. The human brain, however, with its incredible ability to spot subtle differences and anomalies, remains an invaluable tool. This is where projects like Backyard Worlds, Planet 9 come into play, turning the search for our solar system's hypothetical ninth planet and cold, nearby brown dwarfs into a global treasure hunt. The concept behind Backyard Worlds is brilliantly simple and incredibly accessible. The project's website presents volunteers with brief, side-by-side animations called flipbooks, made from infrared images taken by the WISE telescope at different times. Your task is to scan these little movies, looking for any object that appears to move slightly against the static background of stars. This apparent motion or proper motion is a key signature of a nearby object. Distant stars are so far away they appear fixed in the sky, but a cold, faint brown dwarf or a wandering planet within our cosmic neighborhood will have a detectable shift in position over months or years. It's the same principle you use to judge distance while driving near by objects like telephone poles whiz by, while distant mountains seem to move very slowly. By training your eyes to spot these tiny, jumping dots, you become a frontline explorer, sifting through the cosmic static for the telltale hop of a hidden world. The interface is designed to be intuitive, with tutorials that guide you on what to look for and a simple click to mark any potential candidates you find. And the most thrilling part, this isn't just an educational exercise. It's a genuine research platform that has led to spectacular published discoveries. The community of dedicated citizen scientists on Backyard Worlds has already co-authored numerous scientific papers, and their work has identified dozens of previously unknown brown dwarfs, including some of the coldest and most intriguing white dwarf candidates. One of the most remarkable success stories involves a volunteer named Jörg Schumann. While examining flipbooks in 2018, Schumann noticed a very faint object with a slow but distinct motion. He flagged it for the science team, who followed up with ground-based telescopes. The object was confirmed to be a rare cold brown dwarf, and it was subsequently named WISE 2001-157,520 AB. What made this discovery so special was its nature. It turned out to be a binary system of two brown dwarfs orbiting each other, a fascinating and relatively rare find. This demonstrated that the sharp eyes of a citizen scientist could not only find single objects, but could also uncover complex systems that provide critical insights into how these substellar objects form and evolve. Another stunning discovery came from a citizen scientist named Frank Kaiwi. Using a more advanced data mining technique on the Backyard Worlds platform, Kaiwi identified a record-breaking object, a brown dwarf so cold and faint it was at the very limit of what the WISE data could reveal. This discovery highlighted how the project empowers people to go beyond simple visual inspection and engage with data analysis tools, leading to frontier science. These are not isolated incidents. The collective effort of tens of thousands of volunteers has created a powerful human-powered filter, scanning through millions of flipbooks and producing a list of high-priority candidates for professional astronomers to investigate with powerful telescopes like the Hubble, Spitzer, and now the James Webb Space Telescope. Every time a volunteer tags a moving dot, they are potentially pointing the world's most advanced observatories toward a new world. This transforms the abstract concept of scientific discovery into something deeply personal and participatory. You are not just learning about these dark worlds, you are actively helping to pull them out of the shadows and into the light of human knowledge, becoming a part of the story itself. This profound connection between these solitary, dark worlds and the familiar giants in our own solar system is where the study of white dwarfs transforms from a niche curiosity into a fundamental tool for planetary science. Think of it this way: trying to study the intricate atmospheric dynamics of Jupiter is incredibly difficult because of its overwhelming context. It's enshrouded in thick, complex cloud decks, and we're looking at it from the outside in, trying to piece together its internal workings based on what we can see swirling on its surface. It's like trying to understand the engine of a car by only looking at the smoke coming out of the exhaust pipe. A white dwarf, by its very nature as an isolated object, offers us a completely different and incredibly valuable perspective. Because it has no star to outshine it, we can observe its entire atmospheric system as a single, integrated entity, measuring its heat flow and chemical composition directly. It becomes a controlled laboratory in the sky, a simplified model of a gas giant where we can test our theories about atmospheric physics without the complicating factor of stellar irradiation. Consider the mystery of Jupiter's deep interior. We know it has banded cloud structures and a massive, long-lived storm in the Great Red Spot, but the forces that drive these features originate deep within the planet, in layers we cannot directly observe. Our models predict the existence of hidden cloud decks, including a deep layer of water clouds, but they are buried far beneath the visible ammonia ice clouds we see. This is where a white dwarf like WISE 0855 becomes an invaluable key. Its profound cold means that the atmospheric layer where water condenses is not buried deep under thousands of miles of atmosphere. It's shifted upward into a part of the atmosphere that our infrared telescopes can actually probe. By studying the composition and behavior of the water ice clouds on this free-floating world, we are essentially getting a preview of the hidden weather occurring deep within Jupiter itself. We can see how water vapor circulates, how ice particles form and dissipate, and how these processes interact with other atmospheric chemicals in an environment dominated by convection, just like Jupiter's. The white dwarf acts as a natural dissection, exposing for us the inner layers of a gas giant's atmosphere in a way we could never achieve by looking at our own planetary neighbors alone. Furthermore, the relentless and violent weather on white dwarfs provides a pure test case for understanding the jet streams and storm systems that rage on all giant planets. On a world without a star, there is no external heating. The entire weather engine is driven by the internal heat rising from the core and the subsequent cooling at the top of the atmosphere. This creates a perfect, self-contained system for studying convection. The supersonic winds and planet-spanning storm cells we infer on white dwarfs are a dramatic, unadulterated example of the same basic processes that create Jupiter's banding and Saturn's hexagon. By developing computer models that can accurately simulate the chaotic atmospheres of these dark worlds, we are inherently refining the same models we use to understand the climate of Jupiter and Saturn. If a model can successfully predict the distribution of ammonia ice clouds on a white dwarf based solely on its internal heat budget, then we can have far greater confidence when that same model tells us how water and ammonia behave in the deep atmosphere of Jupiter. This cross-pollination of knowledge is revolutionizing our field, turning these cosmic ghosts into Rosetta Stones for deciphering the complex and beautiful atmospheric dramas playing out on all the giant worlds we have ever discovered. Looking beyond the groundbreaking capabilities of the James Webb and Roman telescopes, the next several decades promise an even more profound revolution in our ability to study these dark worlds. The future of this ghost hunt lies in a new generation of observatories, purpose-built with technologies that will transform these faint whispers into detailed portraits, allowing us to not just detect white dwarfs, but to truly see them as dynamic, complex worlds. At the forefront of this vision is a concept known as the Habitable Worlds Observatory, or HWO, proposed as NASA's next flagship astrophysics mission after Roman. Its primary goal is nothing short of historic: to directly image and analyze the atmospheres of at least 25 Earth-like planets orbiting other stars. While its focus is on sunlit worlds, the technological leap required will have a staggering ripple effect on the study of sunless ones. To block out the overwhelming glare of a star to see a tiny, orbiting planet, HWO will need a coronagraph of unprecedented sophistication, a device far more powerful than anything flying today. This same technology, when pointed at a solitary white dwarf, would face no stellar glare at all, allowing it to gather the object's faint light with crystal clarity. Imagine turning a telescope designed to find a firefly next to a lighthouse directly onto the firefly itself, floating alone in the dark. The sheer light-gathering power and razor-sharp contrast would provide exquisitely detailed spectra, enabling us to identify not just the primary gases in a white dwarf's atmosphere, but also trace elements and isotopes that could act as forensic evidence, finally revealing whether a specific object formed like a star or was ejected like a planet. This push for greater detail will inevitably drive the development of even larger space-based infrared telescopes. While JWST 6.5-meter mirror is a marvel of engineering, astronomers are already dreaming of structures with diameters of 10, 20, or even 50 meters, deployed in the cold, stable environment of space. A telescope of that scale would act as a colossal light bucket, catching so many more photons from a white dwarf that we could begin to do something that sounds like science fiction: map its surface. Of course, a gas giant doesn't have a surface in the traditional sense, but we could map its atmospheric features. Instead of a single pixel of light, we might see a small, resolved disk revealing the structure of its cloud bands and storm systems. By observing how the infrared brightness of that tiny disk changes over time as the world rotates, We could create a crude but revolutionary weather map, identifying the locations of major upwellings, permanent storm ovals like Jupiter's Great Red Spot, and the boundaries between its fast-flowing jet streams. We could watch as massive plumes of material erupted from the hot interior, rose through the atmosphere, and seeded new cloud formations. This would move our understanding from the theoretical to the visual, finally allowing us to witness the dynamic and violent meteorology we have only been able to infer from spectra. To push the resolution even further beyond what any single telescope can achieve, scientists are exploring the potential of advanced interferometry. This technique is a masterclass in cosmic cleverness, linking multiple telescopes separated by a great distance to act as one single, gigantic instrument. The resolution or sharpness of an image depends on the telescope's effective diameter. By combining the light from two telescopes placed hundreds of meters apart, you can achieve the resolution of a single telescope as wide as that entire separation. There are already plans for space-based interferometry missions that could, in theory, resolve features on the closest white dwarfs. Imagine a fleet of 4 or 5 telescope mirrors flying in precise formation thousands of kilometers apart, their light combined with nanometer precision. This virtual telescope could discern details on our neighbor WISE 0855 that are smaller than the continent of North America. We could directly observe individual massive storm cells, track the movement of ammonia and water ice cloud decks over time, and perhaps even detect thermal hotspots where internal heat is venting powerfully into the lower atmosphere. This would be the ultimate triumph in the ghost hunt, turning a point of light into a world we can observe changing with the seasons of its own internal climate. The analysis of these dark worlds will also be supercharged by a revolution not just in hardware, but in software. The incredible complexity of the data from these future observatories will demand advanced machine learning and artificial intelligence to decode. These AI systems will be trained on complex atmospheric models to sift through the immense data streams, identifying subtle spectral signatures of exotic molecules or detecting transient weather events that might be missed by the human eye. They could run millions of simulations in parallel, comparing the observed conditions on a white dwarf to different theoretical models of its interior structure and formation history, providing a statistical probability for its origin. This synergy between human intuition and machine processing power will allow us to extract every last drop of information from the precious light of these distant shadows, ensuring that no clue about their nature goes unnoticed. Ultimately, the journey to understand white dwarfs is a journey into the darkest, coldest, and most common realms of our galaxy, and the tools we are building today are the keys to unlocking their secrets. From the wide-angle surveys of Roman that will find them, to the detailed atmospheric dissections by JWST, and onward to the revolutionary imaging power of the Habitable Worlds Observatory and space interferometers, we are constructing a pipeline of discovery that will span this century. Each new technological leap will peel back another layer of mystery, transforming these cosmic phantoms from theoretical specks into worlds with mapped climates, understood histories, and perhaps even answers to the fundamental question of their origin. The infrared future is not just about seeing farther, it's about bringing the darkness into the light, revealing a hidden population of worlds that have drifted in silence for billions of years, waiting for us to learn how to see them. With so much intrigue surrounding these shadow worlds, it's easy for our imaginations to run wild, painting them with a brush dipped in science fiction. We picture them as terrifying navigational hazards, hidden reefs in the sea of stars that could tear a spaceship apart without warning, or we romanticize them as secret outposts for ancient alien civilizations, hidden cities glowing with internal light on a world of eternal night. While these are fantastic stories, the scientific reality is both more grounded and, in its own way, even more fascinating. The truth about encountering a white dwarf is far less dramatic than most space operas would have you believe. Space is overwhelmingly, mind-bogglingly empty. The average distance between stars in our galactic neighborhood is about 5 light years. To put that in perspective, if you shrunk our sun down to the size of a grain of sand, the next closest star would be another grain of sand over 4 miles away. Now remember that white dwarfs are even smaller and darker than stars. The chance of a spacecraft, even one on a millennia-long journey, accidentally colliding with one of these isolated worlds is so infinitesimally small that it's effectively zero. They are not lurking in every shadow, waiting to snag a passing ship. In fact, their profound darkness makes them less of a hazard, not more. Our ability to track asteroids and comets in our own solar system relies on reflecting sunlight off of them. A white dwarf emits no visible light and only a whisper of infrared, making it the ultimate stealth object. But because space is so vast, this simply means we'd be incredibly unlucky to ever wander close to one, not that they are lying in ambush. The other popular trope, that these dark worlds could be thriving hubs for alien life, also crumbles under the harsh light of physics, though it leads us to a more nuanced truth. The concept of an advanced, star-faring civilization building cities on a sunless world is fraught with existential challenges. Without a star, there is no abundant, free-flowing energy for power. Any civilization would be forced to rely entirely on geothermal energy, a finite and dwindling resource on a cooling world, or on nuclear fission, which would require an immense and ongoing mining operation for radioactive elements in a world with no accessible solid surface. Furthermore, the concept of a surface is itself a problem. A white dwarf has no solid ground to build upon. Any structure would have to be a floating platform, constantly battling hurricane-force winds and unimaginable pressure gradients, all in perpetual crushing darkness. The engineering required would be orders of magnitude more complex than building on a planet like Mars. While it's a compelling image, the reality is that a white dwarf offers none of the practical advantages that a rocky planet in a habitable zone would provide. It is an environment of extreme scarcity and hardship, making it an unlikely choice for any civilization, no matter how advanced. However, to completely dismiss the connection between these worlds and science fiction would be to miss the point of why they captivate us. While they may not be practical homes, they are unparalleled narrative devices. They represent the ultimate frontier, the final margin of the map. In stories, they are perfect settings for tales of profound isolation, haunted landscapes, and existential wonder. Think of the mysterious planet in the film Melancholia, a rogue world on a collision course with Earth, serving as a metaphor for impending doom and the fragility of human civilization. Or consider the desolate, icy planetoid in Star Wars. The Empire Strikes Back, where Luke Skywalker confronts his destiny in a cave that is strong with the dark side of the Force. These fictional worlds tap into the same eerie, lonely quality that real white dwarfs possess. They are places utterly divorced from the familiar cycles of day and night, where the very rules of existence are different. Science fiction isn't trying to be a textbook. It's using these concepts to explore human themes of loneliness, survival, and our place in a vast, uncaring universe. The real white dwarfs inspire this kind of storytelling because they are genuine examples of nature's ability to create environments that defy our everyday experience, pushing the boundaries of what we believe is possible. This journey into the darkness forces us to confront a much deeper question, one that goes beyond telescopes and atmospheric chemistry. What does it truly mean to be a planet or a world? For generations, our definition was tidy and sun-centered. A planet was a round object that cleared its orbit around a star. It was a simple, elegant rule that worked well for our own solar system. But the discovery of white dwarfs and other free-floating planetary mass objects has thrown a wrench into that comfortable definition, forcing a philosophical crisis in astronomy. If a planet is defined by orbiting a star, then a white dwarf drifting alone in the void is not a planet. But if you were to magically transport that exact same object into our solar system and place it in an orbit around the Sun, it would instantly be classified as one. This reveals a profound inconsistency. We are defining these objects not by their intrinsic properties, their mass, their chemistry, their physical nature, but entirely by their external circumstances, by their gravitational address. It's a bit like defining what a person is based solely on whether they live in a city or in the countryside, ignoring their fundamental humanity. A white dwarf challenges us to look past the accident of its location and recognize it for what it is, a world in its own right. This semantic struggle echoes a much older and surprisingly emotional debate in our own cosmic backyard, the demotion of Pluto. Remember the public outcry when Pluto was reclassified as a dwarf planet. That was more than just nostalgia for a ninth planet. It was a cultural moment that forced us to realize our categories are not fixed in stone. They are human constructs, and they evolve as our understanding of the universe deepens. The Pluto debate was a preview of the much larger philosophical shift demanded by white dwarfs. It was a lesson that nature doesn't care about our neat little boxes. The cosmos creates a continuous spectrum of objects, from stars to gas giants to icy dwarfs, and our job is to map that spectrum, not to force its rich diversity into a handful of oversimplified bins. The existence of white dwarfs is the final nail in the coffin for a star-centric definition of a planet. It compels us to adopt a more universal, physical definition, one based on an object's mass and formation, that can be applied consistently across the galaxy, whether a world is bathed in starlight or adrift in perpetual night. When we make this mental leap, our entire conception of what a world can be expands exponentially. We have been culturally conditioned to think of worlds as places like Earth or Mars, rocky surfaces under an open sky with sunrises, sunsets, and the potential for landscapes. But a white dwarf is a world of a completely different order. It has no surface, only an infinite, gradual deepening. Its sky is not a dome of blue, but an unbroken blackness. Its weather is not of water, but of ammonia and hot sand. Is it any less of a world if we define a world as a complex, dynamic environment with structure, weather, chemistry, and history? Then a white dwarf qualifies spectacularly. It forces us to decouple the idea of world from the idea of a place you could stand on. It is a world not for surface dwellers, but for beings of the atmosphere, if any could exist there. This redefinition is humbling. It tells us that the template of our own Earth is not the universal standard for what a world can be. The galaxy is likely filled with worlds that defy our simplest imaginations, not just rocky planets and gas giants, but water worlds, carbon worlds, and now these dark, atmospheric worlds, each with its own unique and alien nature. This realization carries a profound cultural and almost spiritual weight. For all of human history, looking up at the night sky has been an act of looking toward light. We navigated by the stars, told stories in their constellations, and searched for other planets in the warm, life-giving glow of their suns. The universe in our mythology was a place of light. The discovery of white dwarfs introduces a counter-narrative. It reveals a hidden, parallel cosmos of darkness. These are not the black emptiness between stars, but dark, substantial places. They are the cosmic equivalents of the deep ocean trenches on Earth, vast, unexplored, and operating on principles entirely separate from the sunlit world we know. This duality, a universe of both light and shadow, of fiery suns and cold, solitary wanderers, enriches our cosmic story. It suggests that the galaxy is not merely a collection of stellar families, but a much more complex and diverse ecosystem, one with a vibrant, luminous half and a silent, dark half, both equally real and filled with their own forms of majesty. Ultimately, the greatest lesson of the white dwarf is one of cosmic humility and wonder. Every time we think we have the universe figured out, it reveals another layer of mystery. These dark worlds remind us that what we see when we look up is only a fraction of what is actually there. For every brilliant star we can see, there may be several of these shadow worlds, invisible to our eyes but shaping the gravitational and chemical landscape of the galaxy. They are a testament to the universe's boundless creativity, its ability to forge environments so alien they challenge our very language. They force us to be better, more imaginative scientists and storytellers. The hunt for white dwarfs is more than a technical achievement, it is a philosophical expansion. It is our species slowly learning to see in the dark, and in doing so, discovering that the darkness is not empty at all. It is filled with worlds, so as we bring our journey into the shadows to a close, let's gather the core mysteries that make Y-class planets so compelling. The first and most defining is their profound cold. These are not just chilly worlds, they are objects that have shed nearly all their birthright heat, cooling to temperatures we experience right here on Earth. Imagine a place in the void of space where the thermometer reads a brisk 80 degrees or a frigid -10. A world with the climate of a terrestrial day, yet existing in absolute isolation. This incredible cold is what renders them so dark, pushing them to the very edge of detectability and forcing us to redefine the boundaries between a failed star and a wandering planet. Next is their elusive, almost ghostly nature. They are the masters of cosmic stealth, emitting no visible light and only the faintest whisper of infrared radiation. Finding one has been a monumental achievement of engineering and perseverance, requiring space telescopes chilled to near absolute zero, just to sense their minuscule thermal glow against the cold backdrop of the universe. They are not merely hard to find, they are designed by nature to evade detection, hiding in the vast, dark spaces between the stars right in our cosmic backyard. And finally, perhaps the most staggering mystery of all is their potential abundance. Far from being rare anomalies, everything we are learning suggests that these dark worlds could be one of the most common types of objects in the entire Milky Way. Theoretical models and the subtle evidence from gravitational microlensing point toward a galaxy teeming with them, a hidden population that may outnumber all the stars we see in the night sky. This means the brilliant tapestry of stars we gaze upon is only half the story. The cosmos possesses a dark, parallel architecture of solitary worlds, a ghostly infrastructure woven throughout the luminous arms of our galaxy. These three pillars, their cold, their darkness, and their sheer numbers paint a picture of a universe that is far more complex and mysterious than we ever imagined, reminding us that our cosmic maps are still missing entire continents of discovery. The next time you find yourself under a clear, dark sky, looking up at that familiar sea of stars, I want you to remember this. For every single point of light you see, there could be multiple dark, unseen worlds drifting in the immense blackness between them. The universe is not just a collection of brilliant suns, it is also a realm of shadows, and within those shadows lies an entire hidden kingdom of worlds, waiting patiently for our technology, our ingenuity, and our insatiable curiosity to finally bring them into the light. Their story is a powerful testament to how much we have yet to learn, a humbling and thrilling reminder that the greatest discoveries often don't come from looking toward the light, but from learning how to see in the dark. I'd love to hear which part of this journey into the unknown captivated you the most. Was it the bizarre weather with clouds of hot sand and molten salt, the haunting possibility of a rogue planet with a warm, subsurface ocean, or the sheer cosmic mystery of these dark, common ghosts? Let me know your thoughts in the comments below, and if you want to join us for more adventures to the farthest reaches of space, be sure to subscribe.